Thank you for the invitation to speak at Digital Innovation in Mental Health 2020. My name is Maria Liakata and I'm a Turing AI Fellow working in the field of natural language processing. I'm a professor at Queen Mary University of London and the University of Warwick. I will talk about my fellowship on creating time-sensitive sensors from user-generated language and heterogeneous content. My fellowship is a 5-year award which allows an extensive program of work. It was one of 5 such awards made in the UK after an international competition. I will do the presentation jointly with the postdoctoral research associate on the fellowship, Adam Tsakalidis, who is also at Queen Mary and the Turing. I will first present the fellowship goals and objectives. Adam will then talk about progress we have made so far. Let me start by first introducing the area and the goals of the fellowship. Individuals continuously produce large amounts of digital content. Textual data in social media and online platforms, but also language and other data from devices such as computers, mobile phones, fitness devices, etc. We call all this data heterogeneous user-generated content, UGC. All of this data contains behavioral cues. Through this fellowship, I aim to create models that capture changes in individuals' language over time. I call this personalized longitudinal natural language processing. I plan to develop sensors for capturing digital biomarkers from language and heterogeneous user-generated content to understand the evolution of an individual over time. I call these time-sensitive sensors from UGC. I want to apply the technology developed to make a significant contribution to mental health by creating new tools based on the sensors, making it possible to assess and monitor conditions in between clinician appointments, and when access to mental health services is limited, such as is the case of the current pandemic. While the methods I propose and the resulting sensors can have a wide range of applications, I have decided to focus on mental health. What is the motivation behind creating these time-sensitive sensors, and why are they important? The focus on mental health is important as, according to the World Economic Forum, mental health disease accounts for 35% of lost work output, twice as much as cancer and more than cardiovascular disease. There is work at the intersection of NLP and mental health showing that signals for the diagnosis of certain conditions can be found in language. Recent work has also shown that increase in emotive content in social media coincides with an increase in incidents as recorded in mental health records. Meanwhile, the clinical community are looking for new and better diagnostic measures and condition monitoring tools. This is especially the case in situations where access to regular mental health services is reduced. By creating sensors that capture digital biomarkers from language and user-generated content, we can employ them as the basis for new clinical assessment tools. The sensors can also help online platforms with post and user moderation activities, helping to better protect vulnerable individuals. I have 2 particular use cases in mind for the technology proposed: identifying changes in cognition and mood instability. Imagine that your computer has an application that allows it to track changes in your language use over time and is able to present you or people of your choice with evidence that there is a sustained change in your linguistic ability. Or imagine you have bipolar disorder and that your device, phone or PC, can combine your written, spoken, and other digital UGC over time and can create a timeline with supporting evidence that alerts your doctor, yourself, or other individual of your choice that a manic or depressive phase is coming up. So how does the work I plan to do fit in the context of natural language processing? Natural language processing, NLP, is the field that studies computational methods for getting computers to perform useful tasks involving human language and identifying structure in text. NLP is also concerned with the insights that such computational work gives us into human processing of language. We have made a lot of progress in NLP, especially in text classification, but also in translation and generation tasks. There are, however, still important missing elements: dealing with small and sparse data, transferring knowledge across domains, and incorporating background knowledge on linguistic structure, understanding what different architectures can or cannot learn, fairness and bias, having an interpretable symbolic representation, enabling better collaborative human-machine process and improving and updating models, resolution of complex linguistic phenomena such as ellipsis or bridging. At least 3 of these 4 permeate the work we plan to do on the Turing AI Fellowship. So what do we need methodologically to achieve these goals? One major objective is creating time-sensitive unified representations of heterogeneous user-generated content. Typically, in NLP methodology, each word in a sentence is represented as a vector learned using word embedding techniques, and these dense vectors are fed into various neural network architectures for different tasks. These word embedding vectors are typically learned by a variant of the skip-ground method, and more recently, context-aware embeddings have been obtained using transformer networks. There isn't usually a sense of time. Recent work has been looking at dynamically evolving word embeddings to reflect word meaning changes over time from different time windows. What is needed here is to create the representation of an individual through both their language and their heterogeneous user-generated content over time, where the two streams are asynchronous. So question 1, how to represent an individual from this heterogeneous and asynchronous data? And question 2, how do we vary this representation through time? Another important objective is to address sparsity in real-world longitudinal datasets while respecting ethical issues. There are not many longitudinal datasets, but we are in a good position as we have been working on the creation of such datasets in past projects. We plan to work with small fine-grained datasets, including fine-grained heterogeneous data from students and people with dementia over several months, and large, less granular datasets with millions of users from online peer support networks such as TalkLife and Mumsnet. All these datasets are sensitive, and we plan to keep them in a safe environment. We are in the process of adding annotations to these datasets. We are also working on generating synthetic data on the basis of the datasets. This comes with ethical issues about how best to represent users. We are working closely with Turing research engineers on secure storage, anonymization, and processing. Future plans will involve liaising with colleagues from the Turing ethics group on appropriate generation strategies to preserve personalization without identity revelation and sharing of synthetic data. Another important objective is the definition of clinically meaningful tasks and quantities to measure over time. We are particularly interested in identifying moments of change for individuals and are focusing on obtaining annotations for these. We want to create a real-world evaluation setting where, apart from working with real-world data, we co-create with stakeholders and especially clinicians. The example on the left is taken from our annotation interface for capturing moments of change. In particular, we want our tasks to be formulated in a way that they can be used to help the creation of new instruments for monitoring and assessing mental health. An important aspect of the work is to create interpretable summaries that summarize moments of change over time and the evidence behind these. The image on the right gives a potential visual perspective of the summarization of topics.
Thank you, Maria. So, where are we with all this? The fellowship only started in December, but we have some prior work that has led to it. Specifically, our work from 2016 was the first to combine language and heterogeneous user-generated data for the longitudinal task of predicting the mental health scale scores of different individuals at different points in time. The method we used at that time that showed that the model was making use of all types of data was multiple kernel learning, and it showed very good results in a very popular evaluation setting. Subsequently, in our ECML 2018 work, we explored appropriate settings for evaluating longitudinal predictions in mental health. So what do we mean exactly by appropriate evaluation settings here? Let us consider some individuals and their instances, which are shown as boxes below the individuals on the slide, and correspond to different time periods. By instance, we mean a pair of features and target values. The features can be things like words that the user has shared on social media or how many miles they have walked on a given day. The target, on the other hand, is the user's mental health score on this day, which we aim at predicting. There are 3 evaluation settings considered in prior work that we will examine here. The first case, this is the leave one user out cross validation. What we do is that we leave one user out for testing or evaluation purposes and we train on the rest. That is three individuals in this example. Good results under this setting could imply that our model has successfully learned an association between the features and the mental health state of a population, and therefore can generalize to any other previously unobserved individual. However, this is a very challenging setting, which is very rarely used in related work. The second setting is called leave one instance out cross validation. So instead of learning a universal model, the idea here is to train a personalized model for every individual separately in order to make mental health assessments over time tailored for this particular individual. A crucial factor that is often disregarded though in the literature is that instances in the training and in the test set have to be from non-overlapping time windows. Finally, the third case, which we called mixed evaluation setting, is the most popular found in related work. What happens here is that the user aspect is totally disregarded. Instead, what we do is that we select some instances for training and some others for testing completely at random from different users. While this setting yields the highest results, it tends to overfit and is not a model applicable in a real world setting. And this is why this happens. Consider this example on this chart. So here on the x-axis, we have the actual score, that is the actual mental health scale score of some individuals over time. And on the y-axis, we have the predictions made by our model. It would seem that our predictions are very accurate since they are very, very close to the diagonal. However, by paying a closer look on the chart, we see that our model actually learns to make the exact same prediction for every single user with very small deviations. So you can see two examples of two users in this chart that are now circled. This means that models that are trained in the mixed evaluation setting are in the danger of recognizing who each user is in a given test set because they have seen instances of this exact same user in the training set. And simply what they can do is that they can just predict the average mood for that user. And it turns out that this average prediction, if compared to the general population, is a pretty good estimate. Thus, we see that the user behavior can vary on an individual basis. And this is very problematic because we cannot effectively model a new user, that is, a user for whom we have no information in the training set. To tackle this, in this fellowship, we propose to build what we call longitudinal user representations. Such representations can bring different yet semantically related features close to each other. For example, consider the location feature. The location I'm currently in is modeled through the longitude-latitude pair. However, the values of this pair are very different compared to someone else's home. What we aim is to learn this mapping across different users. And there are two main settings that we have been working on, the window-based setting and the dynamic setting. In the window-based setting, the representations are learned independently in different time periods. So we can build a user representation for a user on Monday and Tuesday respectively and separately, based, for example, on the locations that this user has been to on Monday and Tuesday respectively. We then try to align such representations and measure the displacement error. In other words, how different the representation, that is the behavior of the user, has been on these different days. In the dynamic setting now, the representations are learned jointly across different time periods. One such example is a sequence-to-sequence model, where the input is a one-hot encoded vector of a user's behavior over some time period, and the task can be to either reconstruct this behavior over the given time or to predict the one-hot user's behavior in the future. Contrary to the window-based approach, we can obtain user representations over time through the vectors that correspond to the hidden layers of the neural network without the need to perform any sort of alignment. We have been making progress in both of these settings and we plan to further explore the properties of each.
Thank you, Adam. We plan to work on a number of different tasks over the course of the fellowship, including data representation learning and synthetic data generation, see the work packages in the first column, anomaly detection and longitudinal prediction, see the second column, and the creation of interpretable summaries from longitudinal user behavior, as well as real-world evaluation, see the third column. You can also read my Turing blog about how this project could help with COVID-19. I could not have done this work without my research team. Apart from Adam Tsakalidis and Federico Nani, who are part of the core research fellowship team, along with 3 PhD students to start in October, I also work with a number of PhD students and postdocs at the Turing, Warwick and Queen Mary University of London in a variety of related topics within NLP and NLP applications. Thank you very much for listening.